We'll go ahead and get started. So for this next section, we're going to talk about data exploration and linked views. This will be a little bit of a shorter section before we move on to visualization critiques to end our afternoon. So if you recall, yesterday I sort of positioned the start of our conversation about visualization within two general processes, sort of these two intersecting perpendicular processes. The first was a process that considered visualization as part of a continuum from data collection to interpretation. And you might recall I said that a lot can happen in the space between, right? So we said that we might start with data collection or recording observations, move on to structuring and cleanup, preparing our data for analysis. Then we do the analysis, and then we visualize the findings from our analysis. This could also be more generally labeled communication. And then beyond that, we have interpretation. And I said that these steps sort of lie along a continuum from well-defined to ill-defined, right? I said that for the most part, things on the data collection end of the spectrum are well-defined in the sense that we have standards and conventions around doing the data collection piece. But things closer to the visualization and interpretation ends are more ill-defined, meaning that we have less control over how people interpret our findings. And so this visualization step is really critical because it's sort of an inflection point between our analysis and interpretation. I also said that perpendicular to this continuum, there's this design thinking process composed of 5 steps: empathize, define, ideate, prototype, and test. And I talked about how design thinking processes, they're characteristically good for ill-defined problems and things that are human-centered. And we talked about how visualization is an ill-defined problem and how it's human-centered and also requires a combination of logical, rational approaches and sort of creative approaches. So I want to return to this conversation today and talk about what these mean in the context of data exploration. And return to this question of why do we use data visualization to explore our data? It's a bit of a rhetorical question because we've already answered this a million times, right? We know that visually displaying data makes it easier to find patterns. That's why we visualize data. And it works because specifically it makes data, complex data, more accessible and understandable by mapping it to experiential knowledge. So about 30 to 50% of our brains are devoted to visual processing. And so we can actually leverage all of those input channels to understand data. So this has significant implications for working with data that might behave in unexpected ways. So there are cases where data that seems statistically identical may actually be very different graphically. An example of this is Anscombe's quartet. Anyone familiar with this? So Anscombe's quartet is a collection of 4 data sets of x and y coordinates. And the interesting thing is that while all 4 data sets are numerically distinct for the most part, they have identical statistical qualities. So they have the same x mean, x variance, y mean, y variance, same correlation between x and y, and same linear regression. Different data sets, same properties. The differences between the data sets become even more apparent, though, when you actually graph them. So if we plot these data sets, we see that all 4 of them have very different behaviors, right? So this top one, we have sort of a random distribution, different distribution for these other 3 here. And yet, just by doing basic statistical analyses on them, it appears that they're identical. So the lesson learned here is that we really need to be cautious of analyses that collapse distributions, data sets, into summary representations. And this includes charts and graphs, right? So we might have 2 representations of a data set. One is a bar graph, and the other is box and plots. And they both tell us very different things. The problem is with the bar graph, we lose a lot of the resolution of detail that we see in this representation. So we can use data exploration to make it possible to not lose that resolution of detail. And one way of building in this possibility for data exploration is interactivity, making graphs interactive. So I'm going to talk about a few different techniques specifically for interactivity, show some examples of each of them. These include zooming and panning, highlighting, brushing, filtering or faceting, elighting, details on demand, and animation. And importantly, and Michelle alluded to this in her keynote yesterday, it's not that we can just do these things for interactivity, we can also do linking with them. So if you recall from Michelle's keynote, we have this idea of linked views, where interaction with data in one chart or one view is mirrored or translated in another chart. So she talked about one platform that she's worked on in particular called Glue. So I'll show you a short video of this. So here we have a display with 3 different visualizations. And as the mouse selects one region and one visualization, it highlights the same data selection in the other 2 visualizations. So this is this idea of linking views. And here we're seeing that in combination with brushing as one particular form of interactivity. So interactivity is important not only because it makes our graphs explorable, but also because it introduces this idea of focus plus context. And this is actually a really important concept in visualization theory. This idea that focus means the user can drill down in detail on one specific aspect of your data visualization. And then context, meaning that you still retain the overall summary view of the data set, right? So you can hold both of these views in tension, a very close reading of your data set and a distant reading of your data set. So these different forms of interactivity enable this idea of focus plus context. So I'm going to show some examples of specific forms of interactivity. So one basic form that we see often is zooming and panning. So this is, well, will it work? Let's see here. There we go. So the basic idea with zooming and panning is that you can use your cursor to move the axes left and right, for example. I can double click and zoom in on particular aspects of the data. And so with the zooming and panning, I can control the context of the view I'm given, as well as control the specific focus of detail that I'm presented, right? So that's zooming and panning. We also have highlighting. So for example, we may have a visualization that has 2 series of data sets, and we can highlight in yellow one of those series, providing us focus on that particular data series while retaining the context of the fact that we have these 2 different data series there together. That's highlighting. We have brushing. So we saw a little bit of this in the glue demonstration. So with brushing, let's say we have, oh, you can't see it. Say we have a line chart here. Down here we have a smaller version of that. a more zoomed out view. And what we can do is actually use our cursor to literally brush over the smaller data series and control the extent of data that's displayed to us. So I can take a very close view of the data in that particular time period, or a very wide view of the data. So that's brushing. Another example, we can see brushing and linking combined. So here we have a scatter plot matrix like we saw in the previous lecture. And I can select a particular region in one of the scatter plots, and it highlights the corresponding data in the rest of the plots, just like that. So if there's a particular aspect of the data that you want to focus on, you can highlight all those data in the other visualizations. We can also use filtering and faceting. So there are two kinds of filtering and faceting. There's side-by-side, which is where you juxtapose data classes using a common axis. And then there's layering, which is a superimposition of data series, data classes with different encodings. So for example, we have side-by-side. So we literally have two scatter plots next to each other. Each scatter plot individually showing one data series, one data class. And contrast that with superimposing your data classes, so layering from kind of faceting. So we have two data series, both encoded differently using color in this case. E-lighting. So this is another common form of interactivity that we see often. So in this form of interactivity, you can focus on a selected item to show detail, while at the same time, the remaining data are shown in summary. So again, this idea of focus plus context, but in a slightly different format. So if I show you this one, this is a collapsible tree diagram. So I think this is you can't even read the text, but this is a tree diagram showing different packages for a software library. I can click on an individual node, and the tree expands to show me greater detail. I can select further nodes to get more details about those nodes. All at the same time, the higher level structure is shown in summary, right? So I can still see the overall structure of the tree at the same time. So these different kinds of interactivity, this idea of focus plus context, really enables you to hold in tension a reductionist reading of data with a holistic reading of data. And this is this idea, again, of close reading of your data and distant reading, right? And some of the best visualizations are able to combine these reductionist and holistic views of a data set. So here's an example of one that does just that. This is a visualization from the New York Times. About temperature changes in Boston. So here we have the red lines, this red path, showing the actual high and actual low temperatures for each day of the year in 2015. The gray here, this middle band, is average temperatures. And then the lighter gray, you can see it, are record highs and record lows. And so you can see a very close reading of the data by seeing the actual data points for individual days throughout the year, at the same time as seeing the average trends for the year, as well as data points for entire recorded history, right? Showing the record highs and record lows. Another form of interactivity is details on demand, which is like e-lighting, just sort of a little different in how it's employed. So here we have details on demand in action when we hover over individual bars in a bar graph. So when I hover over this bar, it gives me the frequency value for that particular bar, right? And it shows me the same for the others. And it highlights that particular bar at the same time. So details on demand. We can use animation as a form of interactivity as well. This is a really interesting visualization that someone put together showing how Americans spend their daily lives. So if I speed up the clock here, as the clock moves, each individual moving circle here represents a single person. And there are these different regions of activity, right? There's shopping, household care, sleeping, eating and drinking, personal care, traveling. And so you retain this view of the individual as they move throughout the day, while also seeing at the same time overall patterns of groups of people, right? And how they correspond with each other over time. So as we move through the morning, this bottom category here is work. So people are going to work. The center region being traveling. So again, focus plus context. We can combine interactivity. So here's one where we can brush and zoom at the same time. So here's a scatter plot with 3 different clusters. I can brush over one particular region of the scatter plot, and it zooms into that region for a closer look. So there are all these different ways of building in interactivity in visualizations. For the most part, though, especially when we're working with scientific visualizations, we don't really have the option of building in interactivity like this into our plots and charts, right? So how can we embed interactivity, or something like it, an exploration, into static visualizations? Can you think of some examples of how you may have accomplished a similar task in visualizations you've made? Think back to what we talked about in multidimensional data, right? So this idea that you can use different strategies to communicate multiple variables at once. You can create multiple graphs of the same data to highlight specific portions of it. You can use a sort of narrative storytelling structure to guide the attention of the user through it. So we can do all of these things when we're creating static visualizations without having to rely on actual point-and-click interactivity. So there are a few particular strategies that we can use when we're working with static visualizations. So these are some things that we've talked about already. Things like small multiples, callouts, so selection and highlighting, filtering and faceting, and multi-form encoding. If we start with small multiples, this is something that we've talked quite a bit about. So this idea, again, of presenting the same data set across similar dimensions, but different slices. So that may be different time slices, for example. Here we have different slices of different markets. So it enables cross-comparison among multiple charts. So this is one simple way of embedding exploration or interactivity into a static visualization, because you're still enabling this idea of focus plus context in a static visualization. It's just not point and click based. Callouts, so selection and highlighting. Another thing that we've talked a bit about. If I have a scatter plot that looks like this, maybe I want to call attention to one particular region of that scatter plot. So what I can do is highlight a small subregion of that scatter plot, and I can even put a call out, a larger sort of a zoomed in visualization showing that particular region, right? So again, this idea of focus plus context without needing point and click interactivity. Filtering and faceting. We've seen a lot of this already. Scatterplot matrix is an example of filtering and faceting, because what we're doing is we're faceting out multiple dimensions that we can do cross comparisons between. So here, each one of these scatter plots represents a different combination of facets, different filtered dimensions. And then there's multi-form encoding. And this is just the general idea that we can take a set of data and visualize it in multiple ways, in multiple charts, right? So we might have a data set that we represent in a scatter plot, as well as a line chart, as well as a bar chart. And we might present all three of these together at the same time. Why might something like this be useful, do you think, multi-form encoding? Can you think of any examples in your own work where you've had to do something like this before? Yeah.
Sometimes I'll set up multiple graphs like this just to decide which one sort of intuitively was the best.
Yeah. So it's a good decision-making procedure. It's also just more generally useful because sometimes we have particular dimensions in our data that benefit from a wide variety of encodings. So it might be ambiguous as to which kind of encoding might be best. And then a more general case being that often we have data sets that require different kinds of encodings at the same time, right? So multiple dimensions in the same data set that need to be represented or encoded differently. So we use this all the time, but it's another form of focus plus context. Okay? Any question about these things? I want to show a couple of examples of packages and tools for R specifically that can be used for data exploration and interactivity. So the first one is something that Ting introduced just a short while ago, actually. This is called Upset R, and it's an R package for basically different visualizations of sets, intersections, and aggregates of intersections. So we saw this already. I'll show you an example of it. So this example uses data about movies. And so with this package, you can create these kinds of visualizations. So different ways of showing intersections. You can't read this on the projector, but these are different genres of movies. And then each of these represents films that cross over these different genres, so intersections of genres across these movies. So this is a useful tool for providing sort of an alternative representation of your data set, especially when you're working with sets and intersections. Another useful tool is something called Trelliscope.js. And so the idea behind this particular package is that you can create interactive trellis displays or small multiples displays of your data in R. So here's an example using car data. And I'll show you the interactive version. So here is a Trelliscope visualization display based on car data. And small multiples, so we have multiple faceted scatter plots here based on different variables. And importantly, you can sort of filter and sort different dimensions, different criteria in your data. There's another example down here. Where there's interactivity. So you can take a scatter plot, for example, and make it interactive, hover over individual data points, and you get details on demand. You can pan and zoom the display. So again, taking a chart you might make in R and actually making it interactive using JavaScript. And then there's Shiny. Anyone here use Shiny? Yeah. So this is a great tool, of course, for creating interactive visualizations. So if you haven't seen Shiny before, here are some examples. So this is k-means clustering in R, and it's interactive, so I can say increase the cluster counts, and it changes the visualization in real time. I can change different variables. It updates the visualization in real time that way too. So making R-based visualizations and data analyses interactive. There's another one that actually uses brushing. So we can actually build in this brushing behavior into a visualization. And it gives me, over here, a list of all the brush points. So Shiny is a great tool for creating packaged interactive visualizations based on native R code. And then there's another tool that you may not use very often, but I'm seeing more scientists use actually, and this is Tableau. Has anyone here used Tableau? Have you heard of Tableau? So Tableau is especially popular in business intelligence, business analytics, very popularly used in corporate settings, but it's being increasingly used in scientific settings as well. And the reason is that it's very useful for very rapidly prototyping beautiful interactive visualizations that you can package and share with other people. So I'll show you a couple of examples. This is an interactive map. I can hover over individual points to get information about stations. I think I can click on individual points here, and it updates, oops, the bar charts down here. I can zoom and pan. So all of this was created using Tableau. Show you another example here. This one showing percent change in deaths from 1980 to 2014 according to particular causes. So we have these different categories: cancer, nutritional deficiencies, infectious diseases, and for each category, chlorophyll maps. So you can hover over individual counties in these chlorophyll maps and get details on demand. So again, created using Tableau. So this is another great tool to actually consider as you're working with your scientific data, because it's not only useful for creating sort of end product visualizations, but it's also really fantastic for data exploration. So say you have a very complex set of data and you don't know what to do with it. You can pull it into Tableau and very rapidly create tons and tons of different kinds of charts. And you can filter your charts, you can do analysis on your charts, and it can help you make decisions about the kinds of charts you might want to actually encode using R, for example, if you want to use that to create static visualizations. Okay. Any questions about data exploration or interactivity? So I had an activity to go with this, but I think since we only have about 10 minutes left until 4:30, I'm going to break here, and in about 5 minutes we'll come back and then we'll wrap up the day with visualization critiques. Does that sound good to people? Okay. So take about 5-minute break.
During the heat map hands-on, I forgot one thing, the correlation heat map. So I just skip it, but I updated the heat map hands-on slides, R markdown file. You can find at the first part there is a correlation heat map if you're interested in the correlation.
Do you want to do that right now, or do you just want to? Okay.